Okay, please go ahead.
Great. So this is part 2 of the introduction to sort of some reinforcement learning, and especially driving into the revisited Rainbow paper that I sort of piqued my interest coming out this last year at ICML. So today I would hope to do a quick review from last week, then try to motivate why I chose the paper, go through some of the variants of DQN for the incremental sort of improvements that they made, and then tackle Rainbow, which is a combination of all of those variants. And then talk about sort of the MinAtar MinAtar environments that sort of reduce the space of the Atari games to be able to compute at at least a reasonable level, and then open up the discussion for applications to potentially neuroscience. So that's sort of the agenda for today. Please feel free to interrupt me at any time. Definitely want to make this as open as possible. Great. So let's go ahead and start. So as a quick review, just the anatomy of an RL algorithm, it's really the mathematical formalism of learning-based decision-making, or the approach for learning decision-making and control from experience. We often try to use this iterative cycle for an end-to-end model where we generate some samples, try to fit that model to estimate the return, improve the policy, and then iterate on that. To fit our model, we often use a Q function or to generate our Q table of state action space to be able to generate sort of this model for an agent to take. Just for some definitions, the Q function here is taking a policy of a state and action in time, where it's then getting the expectation of the state and action of the reward for that state and action. Where we then have, we can iterate, or we can then formalize that to a value function as well. And then we sort of have our reinforcement learning objective. There are two different ideas that you can sort of think about the Q functions and the value functions. If we're given a certain policy and we know the Q value, then we can improve the policy, or we can compute the gradient to increase the probability of taking a potentially good action, A. And so this is all sort of just recall from last week. I want to pause here really quick to see if there are any questions or anyone that sort of has any misconceptions or any kind of questions.
Yeah, I think I always do with reinforcement learning because maybe I never kind of implemented it myself. Fully. So Q is an array where let's think about it as a matrix, right? Where each row could be a state and each column is an action, and then the value on the direct intersection is like what would that action in that state do, or eventually, or like to the long-term value, right?
Yes.
Oh, okay. But is it how it's usually implemented? Let's take chess or checkers or something like tic-tac-toe, like a simple thing. So your state, tic-tac-toe, nine. It's not a binary. It's a binary number, right? It can be encoded by a binary number, 9-bit number, and not all the states are possible. Or are we having all of the possible 2 to the power 9 states?
For our intents and purposes, yes, we're looking at sort of the whole world of state possibilities, but we're taking observations of that state each time to update the Q table for our observations.
So it will be 512 by 9 matrix that we start, because 9 options where to put my cross or my 0, right? Even though some of the options are impossible.
Yes.
Okay. So we want to fill in that table through experience somehow.
Exactly.
Okay. Yeah, thanks. That's
great. Any other questions? Wonderful. So to give some motivation of why I'm sort of interested in revisiting Rainbow, since the introduction of DQN, reinforcement learning has witnessed a dramatic increase as described by Deep Reinforcement Learning That Matters, which is a seminal paper that came out a couple years ago that a lot of people cite. A large portion of these papers propose new methods that really build on the original DQN algorithm and the network architecture, but often adapting methods introduced before DQN that work well enough with deep nets. New methods are typically evaluated on a set of environments that have now become really standard, such as the arcade learning environment, ALE, which is the Atari games that we typically see in a lot of these papers that sort of are nice and flashy for the press. In control tasks such as Mujiko, which is shown in the top, that was developed in 2012, and control tasks on DM control as well. So we have Atari here in the second row, and then a new suite that was actually released last year for more control tasks. However, a lot of these results, well, these benchmarks really have helped evaluate these new methods to standardized manners. They really also implicitly establish a minimum amount of computing in order to be recognized as valid scientific contributions. And this is at a time where a lot of efforts in Black in AI and Latinx in AI are trying to bring people from underrepresented and typically underprivileged segments of society into the research community, where these newcomers are really faced with the normal computational hurdles to overcome if they really wish to be an integral part of the community. So to really put it in perspective, the average week to train one of these models, it roughly takes 5 days to train an Atari game on a standard GPU, where there are 57, I think there are 60 now as of this year. But to report the performance, you usually have to run 5 independent runs. So here are some of the statistics, but it would take roughly, gosh, what is that? That's something like 6-7 years of just single GPU hours to be run on multiple GPUs, and just running the cost of 1 Tesla is around $6,000 in US currency. To give that perspective, the average monthly wage for a Latinx American, excluding Venezuela in this study, approximately, they only get around $330 per week for research. And so that is astronomically difficult to potentially try to even publish in one of these. So what the researchers have done is they proposed 3 different questions. And they wanted to ask whether or not they could arrive at the same quantitative conclusions that their experiments set on a smaller scale experiments. Do they get generalizable to well-known non-arcade learning environments, or are they over-specific to the chosen benchmark? And then is there specific value in conducting empirical research in reinforcement learning, where they restrict themselves to only smaller mid-size environments? And so with these propositions, I'm going to go ahead and pause here before jumping into the 6 different flavors of DQN and how that might help to update. Great. So we're going to go ahead and dive into the first one, which is double Q learning. And so here, double Q learning is to try to mitigate the overestimation bias that Q estimates by trying to decouple the maximization of the action from the selection of the target bootstrap. So here we have, are you able to see my mouse on the screen at all?
Yes.
Yeah. Right. So here we have the standard equation for Q learning, for DQN. But here we have the update step, where we're trying to take a specific time t and add in the specific gradient from the target network, updating it by the gradient of the state itself. With DQN, we have the reward function plus a discount factor that maximizes sort of the action of the Q network given the state and the action. Double DQN here takes a second network and will take the both the max of the current Q network and then run in parallel what the other action will do. So here, what it's saying is it's trying to eliminate the bias that it is overestimating given the certain task. So what it's trying to do is potentially do a little bit more exploring while also taking the maximum values. Here we have the bars of the empirical, or the first, here we have the first results that they showed back in the 2016 paper, where they're trying to show that the bias is not necessarily captured by the single DQN, but the double QN network actually finds that there are less error involved. As you can sort of see that the double DQN has a lot lower error in terms of the result as you increase the network size. To the right, these are the 57 Atari games. I know the words are very small in this, and I apologize. The scale here goes from 0 to 100% improvement on human capacity. So this first dotted line is just human ability to play the game. And then here they also claim on tuning some of the parameters that they have rather than just starting at random variables. So they have a sort of a soft start to help them with the games. But they can improve up to even thousands of a percentage increase, where they're trying to demonstrate that double DQN is better than Q learning in this sense. As an iteration to that, they then came out with a paper in the same year, even though this says 2015, the actual paper was published in 2016 in ICML, and it is about the priority experience replay. So instead of sampling uniformly from the replay buffer, the prioritized experience replay here proposes to sample a trajectory with the probability proportional to the temporal difference error. So to really understand the gains of the prioritization, the real challenge of exploration is when the rewards are rare. So if there are only n states, the environment requires an exponential amount of number of random steps until the first non-zero reward happens. So the most relevant transitions from the rare successes are hidden in a mass of highly redundant failure cases, similar to like a bipedal robot falling over repeatedly before it discovers how to walk. So to use sort of this to highlight the differences between learning times of the two agents, both agents will perform a Q-learning update on the transitions drawn from the same replay memory. And so the first agent will then replay the transitions uniformly at random, while the second agent invokes an oracle to prioritize transitions. Here I didn't put the graph for the comparison between oracle and just a random transition choice, but the oracle greedily selects the transitions that maximally reduces the global loss in its current state. So in hindsight, after the parameter update. So the central component of the prioritized replay is the creation by which the importance of each transition is measured. And without going through a lot of the math, this is particularly stable for incremental online reinforcement learning, such as SARSA, which is a different class of algorithms, and then Q-learning, which is already computing the temporal difference or TD error, and then updating the parameters proportional to some kind of delta threshold. The TD error can really be a poor estimate in some circumstances, especially when rewards are noisy. So here is again the all of the 57 games, and so they're basing the prioritized experience replay in addition to DDQN or double DQN. And so as the research line is still going, it is sort of iterating on this. I want to pause here because I know I just said a mouthful of words. Are there questions here? Great. So building off of prioritized experience replay, we get dueling networks. So dueling networks were really introduced by modifying the DQN network architecture. Specifically, two streams share the initial convolutional layers as we see to the left figure here. But the green layer indicated here is separately estimating the value function of the state, which takes advantage for each action. The output of the two networks is then a combination of the two streams to try to get the best of both worlds. Here I have the updated equation for the Q values of each action, and then what they tested on in the original paper in 2016. They used a corridor environment where they have a random a random environment of preceding increments of the maze. So you want to stay on the path as much as possible and learn the actual path of the maze. And so the agent will try to learn from each of the preceding steps. And so
can you talk more, like, is this when you were talking about double DQN, I was thinking about some kind of a meta algorithm. It's a Q value over Q values, but what do those, like, is this related somehow in idea space, or what are they doing? Dueling, where is the dueling happening? What is
so
one
I
that,
think dueling here is more cheeky in terms of nomenclature, specifically because it is more of just a combination of two networks trying to learn sort of the action space after the convolution of learning the state space. So from my understanding of what the dueling networks are doing is they're trying to pose two ways of figuring out how to take an action after learning the state space, and then trying to combine those probabilities in the Q table to be able to better, or to learn faster than the actual Q or like DQN itself. So it's more of a iterative speed up of sorts, if that makes sense.
so is it because, like, you're making two actions at a time with their own
Yes.
history, and so you're kind of exploring in parallel in a sense?
Yeah, that's a great way of thinking about it.
Okay, thank you.
Yeah, no worries. Again, I put the examples that they have of the 57 Atari games here. What's interesting to note is that the differences between the two here are saying that there is experienced replay or prioritized experience replay in the right, and there's not a prioritized experience in the left. And as sort of this paper line or this research line goes on, there's a lot of mixing and matching of these algorithms, which really motivates why to try to combine as many of these as possible. So here, I know the numbers are extremely small, I apologize, but for I think this is Atlantis as the top game, there's an improvement of 206 or 296%, whereas over here it's like 4,000%. And so it's on just a different order of magnitude and improvement when you add prioritized experience replay. Great. And so now we step into multi-step learning. And this was proposed by Richard Sutton in '88. And it's one of the classic papers for reinforcement learning. But in here, instead of computing the temporal difference error by using only one step translation or transition, they can use a multi-step target, where the trajectory in the update horizon are yielding a multi-step temporal difference. Really, the hallmark of temporal difference method is their sensitivity to change in successive predictions, rather than the overall error between predictions and the final outcome. This is really important, especially when we have more simple tasks it works better on, such as trying to predict weather in a course of a week, or a random fork in a road, or sort of a small decision tree that we had to make. But it starts to become computationally expensive as we go up in complexity of the task. But on the flip side, we go into distributional reinforcement learning, which was proposed in 2017. Here, we have the Bellman equation, which is very standard to try to solve for in terms of a transition space, especially for DQN. If we have some sort of transition between XA and then X prime and A prime, we have the Bellman equation here, which is the expectation of the reward function of the state and action, and then we get a discount effect of the expectation of the Q function of the actual space itself. Here, what they're trying to do instead is they want to find a distribution Z that is characterized by the interaction of the three random variables. Here, the reward, the state action pair, and its random return. By analogy, with the well-known case, they call this quantity the value distribution. And so not being as familiar with this topic, as I was going through, they defined that they have the value distribution of the discrete distribution parameters compose and support a set of atoms. And here these atoms are canonical returns of the distribution. So it's sort of, it is a probability distribution that is being returned, which they call atoms. And so here is an example on the right, where this is the output for Space Invaders, which is the fixed action game where you have a blaster and enemies scroll down the screen. This is the distribution atom that is here. This NOOP is a no action probability, or no observed action probability. The O stands for something, but it's when a player doesn't make a move in that given screen. And so, which is more indicative of how humans play the game rather than a machine, just empirically from what they've been finding in this paper. But these are the probabilities of actually using this in the state space itself. And then down here is the percentage increase that they call this algorithm C51, because they end up finding using 51 atoms in a given space is ideal, is an ideal hyperparameter for distributional reinforcement learning. So one interesting outcome of this experiment was that they found that the method does pick up on stochasticity. And here the difference in stochasticity, just for a refresher, people don't know, in rock, paper, scissors, if you choose rock and I choose scissors, that's going to be more determined if I know what you're going to be doing. If I don't know what you're going to be playing, there's going to be a third chance you're going to pick rock, the third chance you're going to pick scissors, and the third chance you're going to pick paper. So understanding that there's a probability of distribution that you could potentially get for an outcome, that is stochasticity. Here, they describe that Pong exhibits intrinsic randomness, that the exact timing of the reward depends on internal registers, and it's truly unobservable. So they clearly reflect that the agent's prediction over 5 consecutive frames and the value distribution shows 2 models indicating that the agent's belief that is yet to receive a reward. So the agent does not include past rewards, and thus it cannot distinguish prediction after receiving the reward, explaining the relative proportions to the different modes of the Pong game. So here they're just saying that with the distributional reinforcement learning, they are understanding stochasticity and getting more reliable results. That was also a mouthful. I want to pause here if people have questions.
Yeah, this is a little overwhelming.
Yeah, I apologize. I'm trying to not throw as much equations, but maybe
not even equations. So they're introducing some notion of atoms.
Yeah, and atoms is also another just cheeky term that they're using for nomenclature in my mind. It's just a distributional return of what potentially the action could be in that after that given episode. So I guess this was one of the better examples I could pull, because we have Space Invaders going left and right. So the actions of going left and right given this state is going to be higher to potentially go right, because you're going to have something here that will collide with you and give you a negative reward. However, if you do have a probability of doing a laser or a left laser in action or a right laser in action, you're going to want to hit him or hit this enemy or try to avoid it to gain more positive rewards. So here what they're trying to say is, and I think there is other distributions behind it of the right and the left probability, but here no action has probably the biggest return, whereas firing a laser, firing a razor, and going right has less of an action. I don't know.
I do have a question here. I'm sorry if I might have missed this during the conversation. So how is the stochastic probability determined in this case? Like, how do we calculate it here? Like when I'm starting initially, how do I calculate that?
Yeah, so to calculate the stochasticity of the game itself, you usually start either with bootstrapping from a previous example or starting with random values and try to learn it as you use the agent. Because specifically, there's going to be various levels that you can have, especially with, if you think of Space Invaders, how they either might interact and go down and up, or even the types of invaders that might like swirl down or something.
Yeah.
So specifically, you're trying to also learn the stochasticity of the game itself. So in my example of rock, paper, scissors, where it was a third, third, a third, it could potentially be a dishonest dice, where it's not necessarily a sixth, a sixth, and a sixth. It could be some other, one could potentially have a half a chance of actually getting of the value of one, whereas everything else is then lower value.
So in this case, if I say that, like, let's say at a certain period of time, I mean, the probabilities for everything will be determined, right? So I mean, because the agents, they are learning each and everything, all the moves. So do you still think that later on that probability will be of any matter? Will it be of any use later on?
Yes, because you're going to be failing more than you will succeed, especially as you're trying to learn sort of how the environment does, and it's going to really depend on how you structure your reward. So whether or not it's equal probability of going left and right and firing, or if it's better for you to, because you want to clear the agents, I imagine you're going to have a bigger reward for actually hitting one of the enemies and letting it go, rather than letting it cycle through and go all the way back up to the top of the screen.
Correct. Yeah. Okay. That makes sense.
Yeah, no worries. Any other questions before I move on? Great. The last flavor of DQN in terms of Rainbow is called noisy nets. This is another one that I'm not fully familiar with. However, essentially it's trying to add a noisy linear layer in replacing sort of the simple greedy exploration strategy used by DQN. The limitations of using an epsilon greedy policy are clear sort of in games such as Montezuma's Revenge, where many of the actions can be executed to collect the first reward. So Montezuma's Revenge, if I remember right, it's sort of like Temple Run, where you're going back and forth, trying to avoid objects and then collecting a coin or some kind of item for value. And so here what they're saying is in Montezuma's Revenge, the actions must be executed to collect the first reward. So they presented sort of a general method for exploring that significantly improves across many of the Atari games in the architectures that they proposed. They also looked at DQN, double DQN, and then an actor critic method as well, which we haven't talked about, which is fine. But they call this noisy DQN. And although it does improve performance, it also might, this improvement might come from the optimization aspect, since the cost functions are modified. And they needed to modify the function due to adding in this these layers of noise. An advantage of noisy nets is that the amount of noise injected to the network is tuned automatically by the reinforcement learning algorithm. I'm not quite sure how that is done. I need to go back and look into the details a little more, but from my understanding, the amount of noise that they inject into the system is another parameter that they tune, which alleviates the need for standard entropy bonus or epsilon greedy types of explorations. This is also in contrast to many other methods that add intrinsic motivational signals that may destabilize the learning, such as reward shaping, which can very much drastically destroy your model, where it's like if I try to increase the Atari game, for example, or the Space Invaders game, if I increase the reward for hitting an enemy from 200 to 1,000, that might sort of break the model as you're changing the distribution of your reward. Another feature of this approach is that the degree of exploration is contextualized and varies from state to state based on per weight variance. So while more gradients are needed, the gradients on the mean and variance parameters are relatively one another by computational efficiency. They propose that automatic differentiation makes the implementation of this pretty straightforward, and similar randomization techniques can also be applied to LSTM units and are easily extendable to other reinforcement learning methods as well. Here is sort of the median score over games where you have normal DQN and then the noisy nets. And these are for 3 games on the Atari suite that I can't quite remember since I don't have them labeled here. But with that, those are the flavors of DQN itself. And so in the original paper in 2018, they decided to integrate all of the aforementioned components into a single integrated agent, which they did call Rainbow, here outlined in a rainbow coloring, which is cute. They replaced, so without getting into a lot of the details, they construct many of the same algorithms with this step, and they combine the multi-step distributional loss, the double DQN, with the greedy state. They proportionally prioritize replay with the absolute temporal difference error. And then they also added the network architecture and a dueling network to adapt for the use of distributions. When they also replace all the linear layers with noisy equivalents to then garner the noisy net aspects. All of the Rainbow's components have a number of hyperparameters, which can be very vast, and the computational space of hyperparameters are too large for an extensive search, so they perform a limited tuning where they start with all of the, they bootstrap essentially all of the parameters to what was published in the previous papers as best results, and then they use those values to then start exploring. Great. And so these are sort of the classical control problems here. What the authors of Rainbow Revisited wanted to do is use both classical control problems rather than the Atari games, and then also use MinAtar, which I will describe here in a second. So here we have a cart pull on the top left, which is to balance a pull on a cart that an agent can move left and right. So only 2 actions, left and right, trying to keep the pull stable. We got the acrobat, which are 2 arms that are have 2 joints, and then the agent applies a force to the joint between the 2 arms in order to raise the lower arm above some sort of threshold that you produce. On the bottom.
So, DJ, about the
Yes.
cart pull, do you know if anybody tried adding vertical degree of freedom, at least a slight, to the problem?
Sort of, you're saying
Instead
like
of just left to right, going same problem, but instead of just left to right, letting it go up and down a little bit as well. Because I'm asking because there's this thing called, I think, Kapitsa oscillator.
Okay.
Is with the pole balancing, not oscillator, what is it? Pendulum.
Oh yeah.
As if you start jittering up and down slightly, then both of the locations become stable. The down location and the top location as well. So I wonder if it would discover that, given the opportunity, you know, if it. Because when it starts shaking up and down after pulling it up, then it's super stable. No need to go left and right.
Yeah, from my knowledge, I think what you can do is use this new DM control suites to potentially use sort of a physics engine and or something in like OpenGL to be able to model more or less that. From what I know is that Gym, which is the Python package that OpenAI and DeepMind collaborate or put out for a lot of these simple toy models, doesn't have that capability. But I'm sure it probably wouldn't be too difficult to put together. From what I know, I don't know if there is a.
Yeah, sorry for
Yeah, no. You just,
didn't mean to derail, but maybe it's just, I'm just curious.
Yeah, in terms of like a pendulum motion too, this bottom right-hand corner is just the mountain car example where the agent builds up momentum between the 2 hills to try to get to the top rightmost. I'd be curious if you could do a cart pull on top of a mountain car. I'd have to look into that a little more, but it's an interesting problem.
Yeah.
And just to finish this off, we have Lunar Lander, which has is trying to land in between the flags straight up, and then has 4 accelerations on each side to try to stabilize it. Here they investigate the effects of both independently adding each of the components to DQN, as well as removing each of the components from the algorithm as well. And so here we have the results on the classical control problem. Hopefully this is not too pixelized to see, or if anything. To the left are the 4 examples of adding in each of these new iterative aforementioned steps, and then this is taking out each of the steps from Rainbow. So they found, they did find that each of these algorithms does improve with Rainbow in the addition of each of the ones. However, they also found important differences, such that like distributional reinforcement learning, which is to be thought as a positive addition on its own, it doesn't always yield improvements with itself. To contrast to the Atari learning environments, the results of the Rainbow paper in the classical control environments, distributional reinforcement learning only yields improvement when combined with other components. So that's just one of the big caveats. The other one is, although cart pull is a relatively simple task, DQN can be quite sensitive to learning rates in such that it can provide an interesting test bed for optimization or optimizer stability. And so they found that with the use of noisy networks and an MSE loss helped to dramatically help with the sensitivity. And it really seems that distributional reinforcement learning is required to obtain good performance on Lunar Lander. Yes. And then both Acrobat and Mountain Car are sparse reward environments, which are typically good for environments for investigating exploration strategies. And so they observed that noisy networks tend to give a performance gain in both of these environments, whereas Mountain Car appears to be the most difficult out of the two, a fact observed by a couple different papers from past conferences.
So besides lunar lander, sorry,
yeah.
Is the rest is kind of like examples of no free lunch learning theorem, because it's like some simple methods are best as well, right? You don't need to have everything for all of them besides lunar lander, like having everything helps, right?
Yes, yeah, and we actually give this as an assignment in the class as well, where we have the students just perform regular DQN and add in one of these variants, specifically a prioritized experience replay, to try to improve Lunar Lander to even get up to a reward of 200. And so just how the game is defined, here we don't see very great results as compared to a 200 reward function, because I think they define it slightly different than we do in our assignment. But what they're trying to demonstrate here is that even oh, my mouse is on the wrong one. Even Rainbow here is performing extremely well due to the combination of all of the above. What's interesting here is that DQN still performs pretty bad, and this is probably due to the architecture that they use, since they tried to simplify it and use only, I believe, smaller convolutional layers in between the neural net. The exact numbers I didn't write down, but I can go look them up too. But specifically, they still show that Rainbow is best here, and then it's a little hard to distinguish between the other lines, but they're still relatively bounded by Rainbow.
What's very interesting is that the no prioritized one is it's still performing better in most of the cases, like except lunar landing, and I think, yeah, and card pose, yeah. Other than that, I think all the lines for no prioritized, they're showing really good results as well. That's really interesting to see.
What is interesting that they didn't necessarily show, and I tried to find other papers that might help with this, but since this was, I think, preprint in 2009, at the end of 2019, and just published in ICML this year, there's not necessarily different sparse combinations of these types of components. So it's not necessarily showing distributional RL plus noisy, or taking out several of these. They're trying to just iteratively take out what this is. So having no prioritized experience replay is interesting, as it's sort of still getting sort of a bound between
it's
these.
still getting better results. So what you're saying is that we don't have the results for combined architectures, like you said.
It's either
DQN,
that, or I have to dig a lot deeper into their supplemental materials, which can, I think, be 50 pages long, because it's one of the DeepMind papers.
Yeah.
But going to a little more complex example, what this paper introduces is MinAtar, which is mini Atari is the conjunction, but it created 5 different games and tried to take it down to a state space of 10 by 10 pixels. This significantly reduces the cost of this, and I tried to give sort of picture examples of what the games actually look like, just so you can sort of see where they're trying to represent the different states. So Sequest is a game I don't think I've played in a very, very long time, but the others, such as Freeway or Asterix or Space Invaders and Breakout, are all contextualized in a way that is able to utilize this 10 by 10 space. These are able to be trained faster, and they're able to have pixel-based inputs. And so they classify these as mid-level environments between the classical control and the full Atari 2600 games. And so when viewed in aggregate, they can find the results to be very consistent with those of the original Rainbow paper. And the impact of these from each of the algorithmic components can be varied from environment to environment. And so here are the results from the different games. And so here we have Asterix, and they still do the same, adding in all of the components from DQN, and then removing them as well. And so what they find is that the performance of the different components is not uniform throughout all the environments, a finding which is consistent with the results observed in the original Rainbow paper. However, if they were to suggest that a single agent that balances the trade-off of the different algorithm components, their analysis would still be consistent with that of Hessel et al. In the original paper. And then additionally, the last finding is that combining all of the components produce a better overall agent. Nevertheless, there are really important details in the variations of the different algorithmic components that merit a more thorough investigation. An important finding in the work that is shown is that distributional RL, when added on its own to DQN, would actually hurt performance here in Acrobat as in Acrobat and Freeway, for example. So when they have no distributional reinforcement learning, they tend to perform worse. Whereas this is in contrast what it was found in the original paper on the larger simulations. There's another paper that notes that nonlinear function approximators using the distributional reinforcement learning generally produces different outcomes than the non-distributional variants, but these differences are not always positive. So going through my notes. Great. And so what they did as well, and this is just a smaller section, is they try to go beyond Rainbow. When DQN was first introduced, it made use of the Hubbard loss and RMS prop. And these are common practices for researchers, as we know, but the algorithmic design decisions. And so in the spirit of reassessing, they tried to do some comparison between Atom plus mean squared loss versus RMS prop in the Huber loss. And so here it's a little small to see, but what they're trying to show is that in blue, Atom is performing better than RSM prop, and then that the MSC is performing better than the Huber loss. And then these are the 57 games as well, and then improvement by using Atom plus MSC rather than MSM prop and Huber loss. Great. And so just as a conclusion, I know we're getting about 10 minutes to time. On on a limited computational budget, they were able to reproduce at a very high level the findings in the Rainbow paper and uncover new and interesting phenomena. It is much easier to revisit something than to discover something in the first place, as they found, and their intent with this work was to argue that the relevance and significance of empirical research on small to medium-sized environments is still ethical, and that they believe that the less computation-intensive environments lend themselves to a more critical and thorough analysis of performance and behaviors as you look between the actions of the different characters or characteristics of the algorithms. What they really want to say is that by no means are they calling for less emphasis to be placed on large-scale benchmarks. What they're really trying to do is consider the small-scale environments as a valuable tool for investigators and reviewers for reviewers to avoid dismissing empirical work that focuses on smaller scale environments. Hopefully this paper is used as a way to cite to reviewers who have qualms about not being robust enough in their exploration. And so hopefully this is alleviating some barriers for unrepresented communities, which only can make our science advances better. And so with that, I do have some appendix slides from the previous lecture from last week, but I wanted to throw it out there for any questions and or discussion into how might this be related to neuroscience or any kind of data that we use.
Yeah, exactly. That would be interesting. Anyone with ideas or like how could that be applied in your imaging? Well, do you have some feed or some seed ideas?
Yeah. So are you still being able to see the
Yes.
screen?
Yes.
So I found this paper that was published earlier this year, and what they're trying to use is a DQN as a representation of how to learn the state space of an Atari game. So they put 6 people in a fMRI scanner and had them play, I believe 3 different Atari games, and they were trying to for an hour and a half each session. So what they were trying to do is essentially learn the state space of the action rather than the reward policy potentially. And so what they, I believe, just scanning through the paper very quickly, they tried to use the data used to train the network. So as the network learned, the data that was fed into it was the human actions that were given. And then they trained a network in parallel that had no human interaction. And what they found is that it learned very similarly, and then they tried to map where that state space being learned into different sections of the brain, which I believe was the dorsal visual cortex, and then some sensomotor cortex areas as well. And without diving too deeply into this paper, one of my issues with it is that they're trying to claim that the DQN model is learning like a human brain with only 6 samples. But that is one application where they're trying to use sort of some of this knowledge to understand at least representation of state space within the brain itself in a task fMRI.
Yeah, that's interesting. But this goes back to 2015 or even earlier papers by Nicholas Kriegeskorte and others like that, where they when deep learning became successful, they took AlexNet and concepts that AlexNet is learning and tried to compare it with a monkey's visual cortex and like how they are structured, those concepts that the monkey is learning, and so surprising similarities. So this work that you just mentioned is like that, right? With
Yes.
trying to compare one with another. Yeah, that's, and the claim or the sort of that points to that those stacked summations with slight linearity is actually resembling the brain, despite neuroscientists say? Yes.
Yeah, so because I think the big claim that they're saying is that like task representations encoded in it's the dorsal visual pathway in the posterior parietal cortex are encoding the state space of when you learn how to play a game. So that's what they're trying to decouple in sort of where the state space is being learned, both by the DQN algorithm and then in analogy to the brain itself.
But what about the other question, the other way? Can we use this more like we use deep learning as a tool now for image 3D, 4D image processing in neuroimaging rather than as an analogy? Is there any work like that uses reinforcement learning that you're aware of, or maybe?
Yeah, so when I tried to do a quick path or a quick search on that earlier this morning, there's a couple papers out right now that I pulled this one, which I still haven't quite gone through yet, but there's what can classical Atari games tell us about the human brain? And I think this is also by the same authors that of the last paper that I just showed, but specifically trying to link what kind of empirical findings we can get when using these algorithms, and then how can we translate that to how potentially we learn in the algorithm itself? Because now we have all of these different components of a DQN in the Rainbow, and which components are necessary or can be modeled more like what our brain is inherently doing. And so I think that's kind of interesting. What I haven't looked at is if it's just Rainbow itself and adding all of the different components is more like our brain, and that there might be even more components that we don't even know about that we could potentially add complexity to the algorithm that might add it as well. And then at that point, it's just going to be a lot more model-based neuroscience. But from what I can tell is that we are lacking in samples and the ability to do compute 4D data. Even with having DeepMind, they still need upwards of 1,400 hours to produce even the standard Rainbow paper, and they're using state space that is vastly smaller than what we could be using in fMRI and or EEG, just because of the sheer amount of signal that comes through.
Yeah, I wonder if we can encode fMRI into something smaller, not 2 gigabytes samples, and actually learn useful stuff from it.
Yeah.
Then translate back to fMRI, not just with reinforcement learning, but with anything. Like this idea of accelerating computational research by working with smaller models, but still data-driven. That's interesting.
No, I completely agree. I have to do a little more research into that, but I think those are some interesting questions to explore.
Yeah, thanks a lot for this mini series with the 2 lectures, which I assume, based on the silence of most of the call, are super dense, yes. But still very interesting. I'm sure we'll come back to reinforcement learning not once in the future meetings. And next time, Rogers will talk about nonlinear ICA and time contrastive and space contrastive learning. All right, Rogers, you're still up for that. Yeah, you're there.
Sounds good. Yeah, thank you.
Yeah, okay, so that'd be nice. And we'll be connecting the concepts together and having fun. The most important is to have fun, of course, and then everything will come as a result. So thanks for joining, everyone. We're out of time, and we're on time today, surprisingly. I talk to you later, everyone. Bye-bye.
Great. Thanks, everyone.
Thanks for the presentation.
Thank you.